All right. Hi, everyone. We are iGEM Technion 2022, and we are very excited to introduce you to our project, Angel Roots. Can any of you try and think, what do these three plants have in common? They are all traditional medicine, whose bioactive compounds are now widely used in the cosmeceutical industry, an industry that combines both cosmetics and pharmaceuticals. And these are the bioactive compounds that are widely used. So we'd like you to meet the newest member of this family, the Angelica gigas, a seasonal plant grown in Southeast Asia. Researchers have been trying to understand the root of its medicinal properties, and they might have found it. The curcin, a small hydrophobic molecule which is synthesized in the plant from phenylalanine. The curcin was found to be effective against many types of diseases: osteoporosis, diabetes, several types of cancer, but above all, it was found to be a leading candidate for the treatment of chemotherapy-induced alopecia. Alopecia refers to a complete or partial loss of hair. In order to understand the importance of hair for patients, we talked with George Ede, formerly a senior social worker from the oncology department. He told us how hair is one of the last things patients feel they have a sense of control over, and how traumatizing can this side effect of the treatment be. If you look at the chart, these numbers speak for themselves, but we wanted to see it with our own eyes. So we joined with two non-profit organizations who assist children with cancer. With the first, we organized an event for the pediatric oncology department. And with the second, we hosted the first ever iGEM Technion hair donation event. It was great seeing everyone come together for such a great cause, and the donated hair can be used for wigs. But just thinking about wigs in a hot summer day in Israel made us understand that a solution is deeply needed. Two other types of existing solution are minoxidil and cooling caps, but both were found to be ineffective in most cases. So by this point, you might be wondering to yourself, why isn't the curcin on this list? It is the leading candidate after all, and we were wondering just the same thing. Our group envisioned a hair care product containing the curcin. So we then continued and made a market analysis. We discovered that 6.3 million patients are suffering annually from this problem. And by this, we can estimate a market size of around $100 million US. We then continued and wanted to learn how much the curcin we will need in such a product. So we conducted a skin permeability assay. We chose PAMPA, which is a cell-less assay due to its safety, low cost, and efficiency. And as you can see on this plot, we used three controls: low, medium, and high permeability control. The curcin behaved similarly to the low permeability control. And from this, we can learn two things. The first, the curcin does not penetrate too deep into the skin. And the second, we can use this type of information when we optimize a future formulation. So now, we can take the existing price of the curcin in the market, $100 for 1 milligram, and compared to similar products, and based on the market analysis and the permeability assay, we can conclude that the price reduction of 4 magnitudes is needed in order to introduce such a product to the market. How do we plan to do this? Manufacture the curcin in bacterial cells. The curcin makes a very good candidate, being a secondary metabolite with a known anabolic pathway. This will provide a safe, efficient, and cost-effective way to produce the curcin in large scales. So now you understand the motivation behind Angel Roots. And I would like to invite to the stage Bara to discuss biomanufacturing.
Okay, thank you, Matan. And from here, let's look at the decurcin pathway. This is the anabolic pathway of decurcin that is found in Angelica gigas plant. And we wanted to start with the fifth metabolite in this which is called ampeliferone. So we found 3 different enzymes that are responsible of turning ampeliferone to 7-dimethylseparosin and then to decurcinol. And from here, by using a simple non-enzymatic esterification reaction, decurcinol is converted to decurcin, which is our desired molecule. From here, let's look at our first reaction in the biosynthesis pathway, from ampeliferone to DMS. This reaction is catalyzed by an enzyme called U6PT, or prenyltransferase. This enzyme transfers a prenyl group from the donor DMA-PP to ampeliferone and turning it into DMS. So we aim to clone this gene under the RIL-R promoter together with the mCherry, and we're still trying to clone 3 other homologs to this gene. Talking about the second reaction in our biosynthesis pathway from DMS to decarcinol. This reaction is catalyzed by 2 different enzymes called SHIM-D and SHIM-E. They are both cytoplasmatic and originally found in Streptomyces strain. As you can see here in this slide, SHIM-D enzyme catalyzes the reaction from DMS into an epoxide intermediate. And from here, there are 2 options. With the presence of SHIM-E, this intermediate is converted to decarcinol, while with the absence of it, this intermediate is converted spontaneously to a secondary unwanted metabolite called myrmezine. So as you might guess, we wanted to prevent this unwanted reaction, and thus we modeled it. As you can see here in the left, this is the concentration of each metabolite over time, and you can see there's a difference between the concentration of decarcinol in red and myrmezine in orange. This difference could be explained if you are looking at the second graph on the right side that shows the ratio between decarcinol and myrmezine versus the molar fraction of SHIM-E. Let's look at this example. When the molar fraction of SHIM-E is equal to 48% from the total recombinant enzymes in our system, the concentration of decarcinol and myrmezine are equal. Meaning, as this molar fraction rises, there's an increase in the ratio in favor of decarcinol. So we wanted to merge all of these conclusions in our genetic circuit design, and thus we cloned the SHIM-D under the lac regulation in order to control its expression, while SHIM-E is cloned and expressed constitutively. So after we designed our genetic circuit and we built it, according to the engineering success cycle, we have to test it. Thus, we conducted a qPCR test, as you can see here. The transcript level of SHIM-D are higher than the negative control and lower than the positive one. The same thing in the case of SHIM-E, meaning all of our enzymes were transcribed. In addition to this, if we're looking at the fold change between the induced and non-induced system, we can see the transcript level of SHIM-D are really affected by the induction. And indeed, because SHIM-D is cloned under the lac regulation. So to sum up, this is how our biomanufacturing machine will look like. One bacterial strain that contains 2 plasmids, and these 2 plasmids express 3 enzymes. So by providing ampeliferone to this system, it will diffuse spontaneously according to our diffusion model and will be converted to decarcinol. So our following step was to quantify the quantity of decarcinol in our system, and thus we conducted an HPLC test, and you can see here, after we consulted with Professor Ayelet Fishman. This is the standard of decarcinol, and this is our sample. As you can see here, unfortunately, we didn't get the specific peak at the desired retention time and wavelengths. So we wanted to run other iterations with our samples by changing the incubation times with the metabolite, by changing the lysis techniques or also the extraction method, but we didn't have the expertise, and the HPLC tests are really time-consuming. So in order to continue our project, we wanted to present to you how we wanted to quantify our biomanufacturing product. Please welcome Eser.
Thank you, Bala. So, as was just explained to you, and as you've seen in the previous slides, HPLC isn't perfect. And here you can see just some of the disadvantages of the HPLC system. And this led us to develop our own method, the Oracell system. It's a method for quantitative detection of metabolites using an organism's existing pathway, and it's based on a luciferase assay. And as you can see, the same disadvantages of HPLC have now become the advantages of the Oracell system. And on our way to develop a quantitative tool, we saw an interesting phenomenon, as you can see here. The underlying mechanism of the Oracell system is the Hippo pathway. And here on the left, you can see one specific mode of the Hippo pathway, the Hippo off. And here, The YAPTAZ proteins translocate into the nucleus. They bind to the T transcription factor, bringing to expression of our reporter gene luciferase, which gives us a detectable bioluminescent signal. However, there's a second mode to the Hippo pathway, the Hippo-on mode. And here, those same YAPTAZ proteins are degraded, meaning that they can't translocate to the nucleus. They don't bind to the T transcription factor. We don't get expression of luciferase, meaning we have no detectable bioluminescent signal. And based on the literature, we are able to see that dicursin is able to interfere with the Hippo-off mode, meaning that once we add dicursin, the previous bioluminescent signal will now disappear. And we theorize that with the addition of dicursin, we can also interfere with the Hippo-on mode, meaning previously where we didn't see a bioluminescent signal, we can now have a detectable one. And that's precisely what we saw with our results. Here you can see our oracell system with different incubation times with dicursin. And following 1 hour of incubation, the cells not incubated with dicursin in orange, they have a much higher bioluminescent signal compared to those cells incubated with dicursin in blue, meaning that the addition of dicursin was able to lower the bioluminescent signal, and thus we concluded that the cells were found in the Hippo-off mode. And as time went on, at 3 and 10 hours, this gap closed. And by 16 hours, we can see that the trend is completely flipped. That the cells incubated with dicursin, not incubated with dicursin in orange, they have a much lower bioluminescent signal compared to those incubated with dicursin, meaning dicursin was able to increase the bioluminescent signal. And thus, we can conclude that by 16 hours, the transition has been complete, and the cells have moved over to the Hippo-on mode. So now you've seen how the oracell system interacts with dicursin, but we didn't want to reserve it only for ourselves. And here you can see many other molecules that impact the Hippo pathway and could thus also be quantified using the oracell system. But it's not only a quantification tool, it's also a screening method. Any molecule that's able to impact the Hippo pathway should be able to be detected using the oracell system. And one of such molecules is crocin. It's being produced by the iGEM Latvia group this year. It's their first time in iGEM, so we're happy to get to include them. And here you can actually see the sample they sent to us. And because crocin is able to impact the Hippo pathway, it should be able to be detected using our oracell system. And so now, looking back at our framework, you've seen the motivation for our project through the PAMPA assay. You've seen our successes on the biomanufacturing side with the transcription of shim-E and D. And you've seen how we are able to overcome the obstacles of HPLC through the oracell system and how we can now detect dicursin. So now you understand where our project is at its current moment. We can now look into the future of Angel Roots. We weren't satisfied with the yield that we expected of dicursin compared to marmazine, and so we modeled the mutation of the shim-E enzyme to hopefully increase this yield. Following that, we can then move to a larger scale, to an industrial size, and for that, we modeled the fermentation to see the expected yield of dicursin as well as the cost associated with it. And for that, we consulted with Professor Yuval Shoam, who lent his expertise on the fermentation process. And following that, we can then take dicursin to preclinical screening to test the safety and efficacy. And for that, we have our collaboration with the Pharmaceed company. They're a CRO company back in Israel, and they agreed to help us with the preclinical screening once we reach that stage. And so now you've seen the science side of our project. Now we want to look at how our project impacted the world, specifically through education. But not just education, education in a post-COVID-19 world, in a world caught in between in-person and digital learning. And on the left here, you can see the in-person side with a whole bunch of lessons that we gave, specifically to Ukrainian refugees, as well as various high schools that we went and taught about synthetic biology. And all the lesson plans we gave were made suitable for people with ADHD, and we also published them online so future iGEM teams could use them as well. And on the right, you can see all of our digital projects, as well as those in the middle that had a foot in both worlds. Speaking of which, we have our virtual escape room, the hallmark of our education. It's a virtual escape room we published online and sent out to various iGEM teams. We can also see a screenshot of it, and we also went into various high schools, taught about synthetic biology, and then had the students attempt the escape room. And following the first few high schools that we visited, we were flooded with requests. Over 30 high schools reached out to us and asked if we could come to their schools and teach about synthetic biology. Unfortunately, because of the physical distance and the time, we weren't able to reach all of them. And so we held a Zoom with the teachers from those schools. And through both of those methods, through us teaching personally as well as holding the Zoom, we were able to reach more than 600 students, which is truly astounding. We never thought we could reach that many students and teach them about synthetic biology. So now you've been able to see how our project impacted the world, and it wouldn't have been possible without our mentors that assisted us in every step of the way and lent us a hand wherever we needed it, as well as the companies that did the same. And so now you've seen, this is Angel Roots. This is our project. Thank you. And one more thing. If you guys want to hear a little bit more, maybe try out an escape room, another one, a mini one, you can come visit us in the biomanufacturing track, booth B21.